This is an overview of the Toshiba Arm-9 32-bit MCU TMPA910 series. Welcome to the training module on the TMPA910. Here we will introduce the architecture of Toshiba's Arm-9 32-bit MCU, which includes touchscreen interface, CMOS image sensor interface, LCD controller, etc. Based on the ARM926EJ-S CPU core operating at up to 200 MHz, the new TMPA910CRA XBG uses a 7-layer multi-bus architecture. This architecture significantly improves performance compared to other devices operating at similar processor speeds. The built-in LCD controller offers support for TFT and STN display sizes up to 1024 by 1024 pixels. An LCD data process accelerator delivers image scaling, filtering, and blending functions and offers real-time processing for movies at speeds up to 30 frames per second. The TMPA910 device has a multi-layered bus architecture. The new TMPA910CRA XBG has a CMOS image sensor interface that simplifies the implementation of applications requiring image capture. A touchscreen interface further reduces the need for external components in man-machine interface designs. Additional connectivity includes SPI, UART, I2C, I2S, and high-speed USB device, 480 megabits per second functionality. Toshiba has incorporated 56 KB of built-in embedded RAM for program, data, and display memory, boot ROM, and a memory controller that supports SDR and DDR SDRAM. Up to 2.5 GB of linear access space can be addressed. An SD host controller supports high-speed mode SD cards with capacities up to 32 GB. The new microprocessor is supplied in a 361-pin FPGA package. Additional built-in peripherals include a 10-bit analog-to-digital converter, 6-channel 16-bit timer, watchdog timer, a real-time clock, and alarm functionality. The ARM926EJ-S 32-bit RISC CPU core deployed in the TMPA910CRA XBG offers flexible size instructions and data caches and a memory management unit. Here we show details about the memory mapping for the device. The device has 32 bits of CPU address width, 32 bits of CPU data bus width, and a 200 MHz maximum operating frequency. The TMPA910CRA has boot modes determined by the external pin settings. They are: the number 1 is boot memory setting, number 2 is external memory voltage setting, and number 3 is external memory controller setting, and number 4 is JTAG pin setting. This slide describes the JTAG interface with the descriptions of boundary scan and the pins and signals used by the interface. The TMPA910CRA XBG provides a boundary scan interface that is compatible with Joint Test Action Group JTAG specifications and uses the industry standard JTAG protocol, IEEE standard 1149.1, made in 1990, and also includes IEEE standard 1449.1a, made in 1993. The TMPA910CRA has 2 operation modes, external memory mode and internal boot ROM mode, Either mode is selected in accordance with the AM1 and AM0 pin statuses. The clock controller is a circuit that controls all the clocks in the MCU. It has the following features. By using a clock multiplication circuit, PLL, the clock controller supplies a clock of up to 200 MHz to the CPU. A multiplier factor of 1, 6, or 8 can be dynamically selected. The clock gear contributes to the reduction of current consumption. Write access to the registers inside the clock controller is disallowed. State transitions of the clock operation modes is as follows. Set the oscillation frequency for the X1 and X2 pins to 24 MHz when booting using USB. The USB of this microcontroller supports high-speed communications. However, if the USB host does not support high-speed communications, USB 1.1 or older, full-speed communications will be carried out. The boot ROM function does not support clock supply from the USB clock pin X1 USB. The interrupts of the TMPA910CRA have the following features. They support 28 interrupt sources, assigns 32 levels of fixed hardware priorities to the interrupt sources, to be used if multiple interrupt requests of the same software priority level are made simultaneously, enables to set 16 levels of software interrupt priority for each interrupt source, enables to mask hardware and software priority levels, supports two types of interrupt requests, normal interrupt request IRQ and fast interrupt request FIQ, and enables to generate software interrupts. Here we show a block diagram of the DMA controller, which has 8 channels and also has a bus master which is 32 bits by 2. Its priority is DMA channel 0 high to DMA channel 7 low, and first in first out of 4 words by 8 channels. It has a bus width of 8, 16, or 32 bits. Its transfer count is approximately 4095. It supports only little endian type. Here we explain the various types of DMA transfer functions. Memory to peripheral. It uses a burst request in all transactions with a single request. Set DMAC burst to 1. Peripheral to memory. For transactions that are not an integral multiple of the burst size, use both the burst and the single request signals. If the amount of data left to transfer is greater than the burst size, then burst transfer is used. If the amount of data left to transfer is less than the burst size, then the single transfer is used. Memory to memory. The start condition for this type is that the channel commences transfers without DMA requests. And stop conditions for this type is when all transfer data has finished transferring, then disable the DMAC channel. Peripheral to peripheral uses burst request and single request. The NDFC has the following features. It controls the NAND-Flash memory interface through registers. It supports 8-bit NAND-Flash memory devices. It does not support 16-bit devices. Supports page sizes of 512 bytes and 2048 bytes. Includes an ECC generation circuit using Hamming codes for the SLC type. Includes a 4-address 4-byte error detection circuit using Reed-Solomon coding/encoding techniques for MLC type. provides an autoload function for high-speed data transfer by using 32-bit by 4-word first-in, first-out registers together with a DMA controller. Each timer block containing 2 channels of timer circuits is comprised of 2 programmable 16-bit free-running decrement counters. The TIM clock input is used for the counter operation. This clock can be selected from the internal system clock divided by 2, which is FP clock divided by 2, and FS, which is 32.768 kilohertz. The timer clock, TIM clock, is generated by a prescale unit. FP clock divided by 2 is T16, and FP clock divided by 2 divided by 16 is generated by a 4-bit prescaler. T256 is FP clock divided by 2 divided by 256 and is generated by an 8-bit prescaler. The timer can run in 2 different modes: free running mode and periodic timer mode. Here we explain about the UART functionalities. The device has a baud rate generator, transmit first in, first out, receive first in, first out, transmit logic, receive logic, interrupt generation logic, interrupt timing, UART interrupt block, DMA interface, IRDA circuit description, hardware flow control blocks as shown above. A few of them are explained below. A baud rate generator. The baud rate generator contains the internal baud 16 clock circuit, which controls the timing of the UART transmit and receive, and the internal IRLP baud 16 circuit, which generates the pulse width of the IRDA encode transmit bit stream when in the low power mode. The transmit first in, first out. The transmit first in and first out is an 8-bit wide, 16 location deep, first in, first out memory buffer. CPU data written across the APB interface is stored in the first in, first out until it is read out by the transmit logic. You can disable the transmit FIFO to act like a 1-byte holding register. Transmit logic. The transmit logic performs parallel to serial conversion on the data read from the transmit FIFO. Control logic outputs the serial bit stream beginning with a start bit, data bits, with the least significant bit, the LSB, first, followed by the parity bit, and then the stop bits according to the program configuration in the control registers. This module also supports Toshiba's proprietary data format called Free Data Format. The I2C bus is connected to the devices via the I2C 0DA and the I2C 0CL pins and can communicate with multiple devices. This module operates as a master or slave device on the I2C bus. The master device derives the serial clock line SCL of the bus, sends 8-bit addresses, and sends or receives data of 1 to 8 bits. The slave device sends 8-bit addresses and sends or receives serial data of 1 to 8 bits in synchronization with the serial clock on the bus. The device that operates as a receiver can output an acknowledged signal after reception of serial data, and the device that operates as a transmitter can receive that acknowledged signal, regardless of whether the device is a master or a slave. The master device can output a clock for the acknowledged signal. This LSI contains the SSP, comprised of 2 channels, channel 0 and channel 1. Since the two channels operate identically, operational descriptions are provided for channel 0 only. The SSP is an interface for serial communication with peripheral devices that have three types of synchronous serial interfaces. The SSP performs serial to parallel conversion on data received from a peripheral device. The transmit and receive paths are buffered with a 16-bit wide, 8 locations deep, independent transmit first in first out and receive first in first out in transmit mode and receive mode respectively. Serial data is transmitted on the SPO D0 and received on the SPO DI. The SSP contains a programmable prescaler to generate the serial output clock, SP0 clock, from the input clock, P clock. The SSP operating mode, frame format, and size are programmed through the control registers SSPO CR0 and SSPO CR1. The USB device controller consists of the core part called the UDC2 and the bus bridge part called the UDC2AB, which enables connection with the AHB bus. It has the below features: conforming to Universal Serial Bus Specification Rev 2.0, supports both high speed and full speed, supports chirp, USB protocol processing, detects SOF and USB reset, suspend, resume, generates and checks packet IDs, generates and checks data synchronization bits, data 0, data 1, data 2, and M data, checks CRC5, generates and checks CRC16, supports ping, and supports 4 transfer modes: control, interrupt, bulk, and isochronous. The TMPA910CRA contains a serial input/output circuit compliant with the I2S format. By connecting an external audio LSI, such as an A to D converter or D to A converter, the I2S interface can support the implementation of a digital audio system. The I2S contains 2 channels, channel 0, which is receive only, and channel 1, transmit only. Each channel can be controlled and operated independently. The interface to the CMOS image sensor is built in. The CMSI captures data sent from a CMOS image sensor in synchronization with the CMS PCK clock. When the downscaling or trimming function is used, only the required pixel data is captured according to the specified setting. Next, when color converting YUV 422 into RGB, color space conversion is performed at the point when a pixel of YUV data has been captured, and then the converted RGB data is stored in the first in, first out, one after another. At the point when the first in, first out contains data with a specified number of bytes, write completion interrupt INT CMSF is output. This write completion interrupt can be used as a trigger to start DMA data transfer. The color space conversion circuit is connected to the internal data bus, enabling only the color space conversion function to be used independently when the CMSI is not used to interface a CMOS image sensor. In this case, converted RGB data is stored in the first in, first out. This LSI incorporates a color-capable LCD controller, LCDC. It consists of a DMA, first in, first out, and related control logics, a pixel serializer, RAM palette, grayscaler, higher-lower order panel formatter, and panel clock generator. An interface for 4-terminal resistor network touchscreen is built in. The TSI easily supports two procedures: touch detection and XY position measurement. Each procedure is performed by setting the TSI control register, TSI CR0 and TSI CR1, and using an internal A to D converter. The touch detection procedure includes the procedure starting from when the pen is touched onto the touch screen until the pen touch is detected. Touching the screen generates the interrupt INTA and terminates the procedure. After measuring an XY position and an XY position measuring procedure is terminated, return to this procedure to wait for the next touch. When waiting for a touch with no contact, set only the SPY switch to on and set all other three switches, SMY, SPX, and SMX to off. At this time, the pull-down resistor built into the PD6 interrupt PX pin is set to on in this state because the internal X and Y direction registers in the touchscreen are not connected. The PD6 INTA PX pin is set to low by the internal pull-down resistor PXD, generating no INTA interrupt. When a next pen touch is given, the X and Y direction internal resistors in the touchscreen are connected, which sets the PDX pin to high and generates an INTA interrupt. This slide gives you information about the starter kit used for the ARM controller, TMPA910. It has all the enhanced features like J-Link, touchscreen, sound audio DAC via I2S SD card socket, and it also has a 512 megabit SD RAM, 256 megabit NOR flash, and 2 gigabyte NAND-Flash